Hi all, I welcome you to the second installment of our DevOps Simple Projects session. This installment is going to revolve around Docker, another tool of importance when it comes to DevOps. In the previous installment, we focused mostly on Jenkins and continuous integration. The session included a hands-on project around Jenkins, where we learned how to compile a code that is present in GitHub, review that code and analyze the test cases, along with how to build a Jenkins pipeline. If you've missed that session, I'll leave the link in the description box below. You can go ahead and attend that session before you begin with this one. However, there is not going to be any continuation issues if you haven't seen the first installment of this session. This is going to be a fresh new project. And here we are mostly going to focus on Docker images, Docker container, and Docker compose. We are going to speak a little bit about the necessity for Docker, Docker's working architecture, and Docker engine in detail. And then we'll move on to our hands-on session, by the end of which you will learn to pull a Docker image and spin your own Docker container. Also, if you want to learn more about Jenkins, Docker, and other tools and technologies under DevOps, don't forget to check out our DevOps certification training, the link to which I'll leave in the description box below. So without much ado, let's get started. So let's start out a little bit by discussing why exactly was Docker required? Why was it necessary? Now, one of the most common problems that industries were facing at one point in time is that there would have been a developer who's built an application that works fine in their own environment. But when it reaches production, there will be certain issues with that application. Now, why does that happen? This basically happens because of the difference in the computing environment between the dev and the product. I'm pretty sure a lot of you might have faced this hurdle in your experience as well. If three or more developers are working on a certain piece of code, there are certain sections, certain bits which work on your system just fine, but they do not work on the others as well. So this is a problem that we need to address. Meaning small and services meaning services. Now, all of these small services communicate with each other over a network to fulfill one particular goal. For example, if there is an online shopping service application, it can be broken down into smaller microservices like the account service, the product catalog, the card server, as well as orders. Now, this architecture has gained a lot of momentum in the past decade, thanks to its popularity amongst the big four companies, as well as companies such as Facebook and Amazon, all of them adopting this architecture. And why wouldn't they? Firstly, there will be certain applications which are easier to build and maintain when they are broken down into smaller pieces or smaller services. Second reason is, suppose if I want to update a particular software, I want a new technology stack in one of my modules, I can easily do that because the dependency concerns will be very less compared to the application as a whole. Apart from that, there's also the fact that if any of my modules or any of my services breaks down, then my whole application still largely remains unaffected and running. So that was all about microservices. But then again, there are problems, like in everything. Now, microservice is this beautiful thing in theory, right? But obviously in implementation, there would be issues. So a traditional approach to implementing microservice architecture is that there is a host machine, and on top of that host machine, there are multiple virtual machines. Now, each of these virtual machines contain the dependencies for one microservice. Now, a lot of you might wonder, what is the disadvantage here? The major disadvantage here is in the virtual machine, there is a lot of wastage of resources. Resources such as RAM processor, disk space, all of this are not utilized completely by a microservice which is running in these virtual machines. So it is not an ideal way to implement microservice architecture. And right now we just spoke about maybe 3 or 4 or 5 microservices, when in actuality on an industry scale, an app like that would require some 40-50 different services. So real life applications are huge. So at the time, using virtual machines does not really make sense because of the wastage of resources. So these are the two problems that there was before the inception of Docker. So how is Docker solving these problems? So moving forward, let's look at the very same microservice problems implementation. So what's happening here is that there's a host machine, and on top of that host machine, here is a virtual machine, and on top of that virtual machine, there are multiple Docker containers, and each of these containers contain dependencies for one microservice. So what's the difference? Earlier we were using virtual machines, and now we are using Docker containers on top of virtual machines. The difference is that Docker containers are actually extremely lightweight alternatives of the virtual machines. What does that mean now? That basically means that in Docker containers, you don't need to pre-allocate any RAM or any disk space, so it will take the RAM and disk space according to what it needs. It'll take up space according to the requirements of applications. But note that we still have to use a virtual machine here, because the host machine has to be a Linux or a Unix based machine in order to run Docker containers. Docker containers do not work on Windows systems. So if you have a Windows system, you do require a Linux or a Unix virtual machine. Only then you can run Docker containers. And another reason for using Docker containers in a virtual machine is that you want to segregate it from the rest of the host machine, and you want to encapsulate that separately in a virtual machine, because in your host machine, suppose you have around 64 GB of RAM and around a 20 TB of hard disk, and all of your microservices combined will not use more than, say, 20 GB of RAM and 200 GB of hard disk. There is no point in running Docker containers on the host machine. I can configure a virtual machine that provides 20 GB of RAM and exactly 200 GB of hard disk, and I can run Docker containers on this particular virtual machine. Now that is one problem solved. We still have to look at the inconsistencies in computing environments throughout the software delivery lifecycle. That problem. Let me tell you, first of all, Docker containers are actually developed by the developers. So if there is such a case where an application works fine in the development environment but not in the production, Docker containers provide consistent computing environment throughout the SDLC lifecycle. So the same environment will be present in the development, test, and product. So there won't be any difference in the computing environment. So what exactly is Docker? Docker is basically a tool designed to make it easier to create, deploy, and run an application. It uses containers, which are lightweight alternatives to virtual machines, where you don't have to pre-allocate any RAM. Docker containers do not use a guest operating system. It uses the host operating system. So there's the host operating system, and on top of that host OS, there is a Docker engine, and with the help of this Docker engine, Docker containers are formed, and these containers have applications running in them. And the requirements for those applications, such as all the binaries and libraries, are also packaged in the same container. And also remember that there can be multiple containers running on top of the host machine. So this is what a general workflow of Docker looks like. You can see one way of using Docker over here. What is happening is a developer writes a code that defines an application requirements or the dependencies in an easy to write Docker file, and then this Docker file produces Docker images. So whatever dependencies are required for a particular application is present inside this image. And what are Docker containers? Docker containers are nothing but the runtime instance of a Docker image. This particular image is uploaded onto the Docker Hub, which is kind of like the Git repository but for Docker images. It contains public as well as private repositories. So from public repositories, you can pull your image as well as you can upload your own images onto the Docker Hub. So from the Docker Hub, various teams such as the QA or the production team will pull the image and prepare their own containers. So whatever dependencies that are required for your application is actually present throughout the software delivery lifecycle. And that solves your first problem. So this is another way of using Docker. Previously, you saw that the images were used and those images were uploaded onto the Docker Hub, and from Docker, how various teams were pulling those images and building their own containers. But Docker images are huge in size and require a lot of network bandwidth. So in order to save that kind of network bandwidth, we use this kind of a workflow over here. We use Jenkins servers or any other continuous integration server to build an environment that contains all the dependencies for a particular application or a microservice. And that build environment is deployed onto various themes like testing, staging, and production. So here the developer has written some complex requirements for a microservice in an easy to write Docker file. And the code is then pushed on to the Git repository. And from the Git repos to continuous integration servers like Jenkins that will pull that code and build an environment that contains all the app dependencies for that particular microservice. Now, that environment is deployed onto the testing, staging, and production. And in this way, whatever requirements are there for your microservice is present throughout the software delivery lifecycle. So right now I want to touch up on certain components of Docker. First of all, this ORCID registry is the Docker registry, and it's nothing but the storage of all your Docker images, which can be stored in public repos or in private repos. These repositories can be present locally or can be present on the cloud. Now, Docker provides a cloud-hosted service called the Docker Hub, which we have discussed previously. You can actually pull an image and prepare your own containers at the same time. And you can also write an image and upload that onto your Docker Hub and upload that into your private repo or a public repo. So the next thing I want to talk about is Docker images and containers. Now, images are nothing but read-only templates that are used to create containers. Now, these Docker images contain all the dependencies for a particular application or a microservice. You can create your own image and upload that onto the Docker Hub. And at the same time, you can also pull these images which are available in the public repos and in Docker Hub. Moving on, we have Docker containers. Now, Docker containers are the runtime instances of these Docker images. They contain everything that is required to run an application. And at the same time, it is also possible that more than one image is required to create one container. All right. So for better understanding of the Docker images and the Docker containers, what I'll do is I'll go back to my Ubuntu box and I will pull a CentOS image and I'll run the CentOS container. So let us move forward and first install Docker to my Ubuntu box. So here what I'm going to do is first I'm going to update all my packages. So I'm going to type sudo apt-get update, put in the password, and here it begins. All right. And with that, it's done. So let's clear the screen. So let's install Docker by using apt-get install docker io. Yes. And this is then going to take some time. So with that, Docker is installed. We're just going to start our Docker service. So sudo service docker start. Then let's go ahead and check our system status. So systemctl status Docker. And as you can see, our Docker engine is running. So now what I'm going to do, I'm going to pull a CentOS image from Docker Hub and I'm going to run that CentOS image. So sudo docker pull and the name of the image, which is CentOS. And it has started. First, we'll check the local repository for the CentOS image. If it doesn't find it there, then it will go to the Docker Hub for the CentOS image and it will pull the image from there. So it looks like we have successfully pulled the latest CentOS image. So now let's try to run this. So sudo docker run it. Alright, so with that we are inside the CentOS image and you've run it. So now you're in the CentOS container. Now I'm just going to go ahead and exit this. With that, I'm going to clear my screen and hope you guys have followed me so far. If you have any questions, feel free to drop them in the text box and we'll be happy to get back to you. So now let us recall what we did. We first installed Docker on Ubuntu, and after that we pulled a CentOS image from Docker Hub and then built a CentOS container using that CentOS image. So now we are going to move forward. So the next thing I want to talk about is a little something called Docker Compose. So let us understand what exactly does it do. So it'll be easier for us to understand what it is. It basically composes multiple different applications on various containers. So suppose you have different applications on various different containers and all of those containers are actually linked together, which you don't want to execute each of those containers one by one, but all together. And you can run all of those containers using a single command. So that is where Docker Compose comes into the picture. With Docker Compose, you can actually run multiple applications present on various different containers with one single command. As an example, you can imagine you are able to define three containers, one running a web app, another running a Postgres, and another one running your Redis in a YML file, which is your Docker Compose file. And from there, you can actually execute all the three containers with one single command, that is Docker Compose up. So let us again understand this with an example as well. So this is my Ubuntu box. We have to install Docker Compose here, but before that, we have to install our Python pip. So sudo apt-get install python-pip, and here we go. Y for yes. And with that, I think we are almost done extracting templates. Right now we are unpacking libraries. With that, we're done. Let's clear the screen, go up. So now let's install Docker Compose. So sudo pip install Docker Compose. So I'm just going to clean it and I'm going to create a directory called nginx. So what I'm going to do, I'm going to first go into the folder where I have my Docker Compose file. So I'm going to open my Docker Compose file in the VI editor and show it to you guys. So it's a fairly rudimentary Docker file, but it should be enough to give you an idea of how this thing works. First, we are specifying the version of our Docker Compose, and then we are going down to define our services. So we are using two services. One is a web service and one is a database. For both of them, we are using the official images. For web service, we are using the official image of Nginx, and for database of MySQL. Then we are defining our ports. So basically what we are trying to do is we're trying to establish a connection between the 3306 port of my local machine to the 3306 port of the Docker container. And then finally, we have our environment credentials. So that is all. I'm going to exit the Docker Compose file. And now we're going to run it and see Docker pull those images. So Docker Compose FNF, name of our file, up, and you can see first try to create a network with the default driver, then it's going to pull both the images and everything that it contains. And it's going to do the same thing for the MySQL database. It's going to take a while, so kindly be patient. This file is taking a little longer to get extracted and then pulled. Now it's creating an Nginx database and setting up the Nginx web server. So now if I type Docker images, you can see both of our images are here. We have MySQL and Nginx. And that is how, with the use of Docker Compose, you define and run multi-container Docker applications. You use a YAML file or a YML file to configure your application services. And then with a single command, which was the Docker Compose up command, you create and start all the services from your configuration all at once. You run this Docker Compose up command and the Compose will start and run your entire app. With that, we've come to the end of the second installation. Stay tuned for the third and final installation of this DevOps project session. I'll take your leave for now. My name is Upasna. Thank you and have a great day.